everyone, I'm Ying and working in the SN systems. Today I will give a lightning talk about compiling your code faster using the program repository and Ccache together. The program repository is a research project and aims to improve turnaround times. It reduces the compilation time by reusing previous compiled function and global variables. It reduces duplication by centralizing program data in a repository. The functions and global variable fragments are shared across multiple translation units. This slide shows some repo-related available materials, which include Git repository, previous talks, and a poster. To make client support the program repository, we touched the LVM optimizer and backend. We add 3 passes in the optimizer and support to output the repo ticket file in the backend. I will not explain the details here. Please refer to the previous talks. From the diagram, we can see that the repo mainly reduces the backend compilation time. Ccache is a compiling caching tool that uses texture hashing of the source files. The whole module needs to be exactly the same in order to the cache to hit. Compared to the Ccache repo reuse at function or global variable level, we could using the repo and Ccache together to build your project faster. If the file is unchanged, the corresponding ticket file in the cache can be directly used without recompile the source code. If the file is modified, the repo compiler will try to reuse the function and global variable fragment, which are stored in a database file. This table shows that the program repository reduces the backend compilation time for both changed and unchanged files, whereas Ccache reduces the whole compilation time for unchanged files. When Ccache is used to build a large project, the cache can quickly become invalid due to the frequency of header file changes. Therefore, the repo and Ccache together achieves much faster builds than using either of them individually. The LVM and client project is used to show the benefits of using the repo and Ccache together. The project is built at points through its commit history. The completion time is measured by adding time tree to all files and analyzed with client build analyzer. 4 configurations are measured: ELF, repo only, Ccache only, and repo and Ccache together. This graph shows the full build time contributions. For 6 consecutive days, the first commit of each day is selected to test the compilation time. The leftmost build is with empty Ccache and program repository. Each of these commits is built in turn from left to right, keeping the Ccache content and the repo database between them. In the full build, the compiled all the changed and unchanged file for each commit. We could see the front-end compilation time can be reduced when enabling Ccache, and the back-end compilation time can get further reduction when targeting on repo. This graph shows the incremental build time contributions. Compared to the previous slide, the compiler only builds the changed files. Since Ccache cannot reduce the compilation time for the changed file, 4 configurations has a similar front-end compilation time. However, the back-end compilation time is reduced when targeting on repo. We can see, except the first commit, the repo and Ccache together gets the shortest compilation time. In summary, program repository can improve the build time when Ccache cannot. For build, up to 62% reduction compared to the ELF. For rebuild, up to 76% reduction. Now I move on to future development. We need to implement missing compiler features, such as debug information and exception handling. Also, a program repository linker is currently under development. Okay, this is the end of my talk. I hope more developers could use and contribute to the repo project. Thanks for listening.
Hi everyone, my name is Matt Morehouse and I work at Google on the Dynamic Tools team. Last year I presented to you GWIP ASAN, which is our memory error detector for production. This year I'd like to present GWIP TSAN, which is an extension of GWIP ASAN that adds data race detection. GWIP TSAN is a recursive acronym. It stands for GWIP TSAN will provide thread sanity. More specifically, it's a probabilistic data race detector that we're working on, built on top of GWIP ASAN. Now, GWIP ASAN integrates with whatever memory allocator you use. You simply splice a tiny fraction of allocations to GWIP ASAN, and by adjusting this sampling rate, you can achieve as low overhead as you want. Allocations sent to GWIP ASAN get buffer overflow and use after free detection. GWIP ASAN does this using guard pages and by protecting freed memory, but it does not detect any data races. For that, we need a new mechanism. GWIP TSAN uses some ideas from Microsoft Data Collider to achieve this. Data Collider works by setting a breakpoint on a random memory access. Then when that breakpoint fires, it removes the breakpoint and sets a watch point on the memory that was accessed. In this case, a watch point is set on RACI counter. It then waits, and if while that thread is waiting, another thread triggers a watch point, it knows that a data race has occurred, and it will report it. If a watch point does not fire while we're waiting, it simply removes the watch point and continues execution as usual. So GWIP TSAN uses this idea from Data Collider to add data race detection to GWIP ASAN. It periodically sets watch points on GWIP ASAN allocations, and then when it detects that concurrent accesses to the same address have occurred, with at least one being a write and at least one being non-atomic, it reports a data race. Now, a key difference between GWIP TSAN and Data Collider is the mechanisms used for setting watch points. Data Collider uses debug registers for this. This allows them to trap on accesses to specific addresses. However, there's only 4 debug registers, which severely limits the number of watch points you can set. It also will conflict with any tools that use debug registers for tracing or other things. So for this reason, GWIP TSAN uses mprotect prot none and a segfault handler to do watch points instead. This does have the unfortunate side effect that it will trap on any access within the same memory page. So even if you have 2 threads accessing different addresses, and there would never be a data race in this case, you'll still hit watch points from both. But the upside is you get unlimited watch points, and there's potential use of Intel P keys to reduce the number of unnecessary traps. Now, we've hit a couple of challenges while implementing GWIP TSAN. The first one we've run into is dealing with atomic accesses. We don't want to report a race if only atomic accesses are involved in the race, because it's not really a race. But how do we tell if an access is atomic at runtime? Our current solution for this is to embed a table of atomic access instruction addresses in the binary itself. Then at program startup, we can read the table into memory and use it to check if any access is actually atomic or not. The other issue we've run into is dealing with system calls. Since we use prot none memory as our watch pointing mechanism, whenever we pass watch pointed memory to a system call, it will fail with eFault. Our current solution for this is to intercept syscall wrappers and to remove watch points before doing the syscall itself. This is straightforward to do, but it does involve a lot of work to find out which syscalls we actually need to intercept. So thank you for attending my talk. I'm happy to answer any questions you have, and I also would be interested in any feedback you have on our approach. Thank you again.
Hi, I'm Andrew Lytkin, and I'm going to be talking about finding and outlining similarity at the IR level. We all write similar code, whether we intend to or not, whether it's copy-pasted code or rewriting the same section but just changing the variables around. But what about code like this? These aren't really the same, are they? Well, they sort of are. It is a loop, and the statement in the conditional is true when the variable it or variable x is a 1. So there's something deeper here. So let's use the compiler to peel off the upper layer and look at the underlying LLVM IR code. It turns out the calculation inside the conditional generates the same IR code, and you didn't even mean to do that. It turns out these sorts of similarities are quite common. In the LLVM test suite, if we could deduplicate these similarities, we reduce our instruction count per file by 3.8% on average. It would be great if we were able to work with these structural rather than identical similarities, where we're performing the same set of operations on a given set of inputs. I've been working on a framework for finding these similarities at the IR level. It accepts a module and outputs the regions of similarity, and then exposes them to the rest of the compiler through a new pass. I've also developed 2 different applications for leveraging this new framework. So, how do we find similarity? Well, it starts with the instructions. Rather than looking at the values of the operands, we look at instructions opcode, instruction type, operand types, and extra parameters to create an unsigned integer representing that instruction. This lets us represent the entire program as a string of unsigned integers that can be passed to the suffix tree, which is the data structure that can find repeated substrings in O(n) time, making it a great tool for finding similar sections of the program. If you want a more detailed explanation on how the suffix tree works, Jessica Paquette has a short explainer in her talk about machine outlining in 2016. Now that we have the repeated substrings, it doesn't mean they're performing the same operation. We need to be able to create a one-to-one mapping of the registers from one set of instructions to the other. In this case, from register C to register A and register D to register C. Once we've determined that candidates are similar to one another, we can group them by their structure, and these are the outputs of the IR similarity identifier. This is an algorithm with very discrete steps. We could replace any one of these steps with a more sophisticated similarity matching algorithm, allowing for more benefits than for any application that is utilizing the framework. Additionally, we can see how there's potential to generalize this model. An instruction can become just some unit that can be serialized into a list to be analyzed by the suffix tree, allowing us to find similarity at many different levels of the compiler. So let's move into applications. The first is a visualizer for similarity in a module. It accepts the similarity and then outputs a similarity report. In this case, we have the program on the left with the similarity groups highlighted in blue and gold, and the corresponding JSON file on the right with an entry for each similarity group. With this JSON and some debug information, we can create a visualizer for similarity in IR code and source code since we can link it back to the source. This sort of strategy could help assist programmers in refactoring efforts and help maintain a clean code base. Now, looking at the code can only get us so far, so the second application is an IR outliner, which allows for code size reduction at the IR level that can be redeployed to any target. It accepts the similarity groups from the IR similarity analysis pass and outputs code that has deduplicated these similar regions of code. In short, the outliner determines that the benefit of outlining these regions in a similarity group outweighs the cost of creating a new function containing that region of code. And then, if it does, it extracts each section into its own function and consolidates them into one function, replacing those regions. More detailed implementation details can be found on the mailing list, and this is currently in review. With our initial implementation of the IR outliner, we get 1% reduction on average with the LLVM test suite, with getting gains of up to 60% in certain micro benchmarks, and 1.3 reduction in CT mark. Looking at CT mark a little bit closer, we can see that we get up to a 5% reduction in consumer typeset, with a few reductions due to underestimates of the number of needed instructions with our current cost model. So you might be asking, why don't we just use the machine outliner? Well, like we discussed before, outlining at the IR level finds gains for any target, where we need target-specific implementations for the IR machine outliner. Additionally, this new method finds a structural similarity over the exact same instruction similarity needed by the machine outliner, finding different opportunities for code size reduction. So you might also be wondering how this compares to the IR outliner proposed in 2017. In short, these two implementations are not that different. However, this new IR outliner is backed by the more accessible similarity framework. In the future, we hope that this framework can be expanded upon to become a more general similarity detector throughout the compiler to leverage similarity to inform better code generation and size reduction decisions. Thank you, and I look forward to your questions.
Hi, I'm Daniel Grunberg, and today I will talk about generating -cc1 command lines from compiler invocation instances. I started this work as a remote summer intern at Apple. Let's get started. First, let's talk about why we did all this work in the first place. and the answer to that is module support, and I'll explain to you why. As a quick reminder, modules replace textual precursor includes with imports of serialized ASTs found in .pcm files. We're interested in explicit module builds enabled by Clang ScanDeps, which is a tool that was presented by Michael Spencer and Alex Lawrence at the 2019 Brussels developer meeting. Clang ScanDeps scans a project and discovers the modular dependencies within it and reports them back to the underlying build system, along with the command lines that can build the module. Let's go through an example. Clang ScanDeps starts scanning and discovers translation unit A, which depends on the transforms module, which in turn depends on IR and analysis. Next, we find B, which is compatible with A and also depends on transforms. Because they are compatible, we can reuse the same set of modules. Next, we discover C, which also depends on transforms and transitively on IR and analysis, but it's incompatible with A and B, and therefore it needs an entirely new set of modules. Clang ScanDeps is a parallel tool, so we might discover the dependency on transforms either through A or through B first, and this would lead to reporting a different command line to the build system. This is bad because non-deterministic command lines are confusing for the build system. And the reason why is that the build system believes the modules to be invalidated every time the command line changes, and therefore it will rebuild the modules on every scan potentially. Clang ScanDeps has access to compiler invocation underlying each translation unit. And what we want to do is to be able to generate a deterministic command line from first principles based on the compiler invocation alone. But before we talk about that, let's talk about the changes that were necessary to the CC1's option parser in order to enable this new use case. We added these mix-ins to the table gen definitions that can be attached to the option declarations. These specify how to parse the option and conversely how to generate a command line option for it. The major categories are displayed on the slide. I'll give you now a few seconds to read through them. TableGen processes these options into macro definitions. I've highlighted the important fields. The key path is the subfield of compiler invocation for which this option is responsible for. Next, we have the normalizer. The normalizer takes the argument list and is responsible for extracting a value suitable for storage in the key path for this option. Finally, we have the merger, which takes this value and stores it in the key path in whatever way is correct. Let's talk about how we use these macro definitions to generate deterministic command lines. We use the same macros, but I've highlighted a slightly different set of parameters this time. The key path is still the underlying subfield of compiler invocation. But now we have the counterparts of normalizer and merger, the denormalizer and extractor. Respectively, the extractor is responsible for extracting a value suitable for consumption by the denormalizer from the key path. So once the value is extracted from the key path, the denormalizer can consume it and generate an option for CC1. People add options somewhat frequently to the front end, and we didn't want this behavior to accidentally get broken in this process. So the first thing we did was move all the subfields of compiler invocation into their own .def file databases. And this enabled us to implement the following check. Once a compiler invocation is parsed from a command line, we generate a command line.
Hello, I'm Aditya. I want to introduce a fast algorithm for global scheduling in SSA form. This is a Midland optimization. It is more like a generalization of GVN hoist and GVN sync, but we have more like improved cost model and some very interesting stuff. We're using modern data structure. We augment the SSA to help find the opportunities much faster. And it also uses the DJ graph, which helps fast liveness analysis in SSA form. So a little bit of insight into how the SSA has been augmented. At each branch or branch out or merge point, we insert specific nodes. On the branch out, we insert a node which we call as alpha nodes, which keeps track of the live out of variables. And if the node has like 2 branch out, then the alpha node will have 2 entries. And the interesting part is these entries track the identical values. Like we compute the GVN of those values, and those args are filled with identical values. So essentially, if the nodes have complete full entries, that means that that variable is anticipable at all the points, all the successors. And the opposite holds for, similar things hold for the branch in, where we insert phi nodes in general. Here we call them as beta nodes. So if the incoming values, like identical incoming values from all the predecessors, then that node will be filled. And this helps figure out which instructions can be scheduled without the concern for safety and especially for scalar values. This actually helps schedule instruction to different basic blocks. The cost model is based on liveness of virtual registers. The goal is to reduce register pressure. So we only schedule, like move the instructions to a different basic block in case the register pressure either reduces or does not change. So after this global scheduling pass, the overall live range will be less. And this is reflected in the register, the spill cost, the total number of spills when we run the benchmark. Global scheduling has essentially 2 parts. One is hoisting and followed by syncing. We do the hoisting first because that uncovers more opportunities, and then syncing, because syncing does not have so many opportunities when we are running the benchmarks. Here are some interesting results. We saw improvements in SPEC 2006 benchmark. The most impactful one was MILC, where we saw 15%, and LBM has around 7%. Others 2-3%, which are also quite meaningful. The patch is on LLVM Fabricator, and the references are like GVN Hoist, and GVN Sync has some ideas there as well. This patch is up for review. This is a slightly older work. You can see from the diff number, it's 32,000. It's been a few years when this patch was submitted. So I would request people to go and review the patch. Thank you.
Hello everyone, I'm Hideto Ueno, a student at the University of Tokyo. I'd like to talk about implicit path dependencies and effectiveness prediction. Here we want to predict effectiveness of optimization paths. We try to reduce compile time by using machine learning methods in the path pipeline. So let's get started. First of all, LLVM has a lot of optimization paths. But do you know how often current optimization paths actually modify the program? In this chart, x-axis indicates kind of paths, and y-axis indicates the probability of changes. As you can see it, the probabilities are basically low. We are investing time in optimization paths which do not success. So we want to improve this situation by skipping such paths dynamically. So the motivation is to skip paths to save compile time. I'd like to explain how optimization pipeline works now. In this example, we first apply the pass1, and there is no change. And next, pass2 changes the program, and so on. In this example, pass2 and pass5 modifies the program. If we have an oracle which predicts these results beforehand, we can skip the passes and save compile time. Therefore, we want to create such an oracle by machine learning method. We accumulated data from benchmarks and trained the model. As inputs of the model, we used code future and recent past result. I will explain later. We use some static counters as code future. For example, the number of instructions or number of basic blocks or something like that. As another input, we used path dependencies. Let us consider this example. In the current path pipeline, there is a point where loop unroll and SROA are executed successfully. The second SROA is mostly used for eliminating small arrays created by loop unroll. So if the first loop unroll doesn't success, the SROA doesn't success for the most cases. We want to encode this kind of logic into machine learning models. So the prediction model takes recent past results and the code future. Then model returns the predictions for several next passes. This program itself is binary classification, so we can apply existing methods. We embed this model into specific points in the path pipeline. Let's take a look at how it works. First, we run some passes. When we reach to the specific point, pass results and the code features are passed to the predictor, and the predictor returns the predictions. So we can skip passes based on the predictions. In this case, predictor says that we can skip 4 passes, and we repeat this until the end. This is the current result. We run experiments on CTMark. We confirm that we can reduce the compile time. And there is a hyperparameter which defines the aggressivity of the method, and you can select the parameter as you want. For some cases, the execution time increases because too many passes are skipped. But I believe the result basically look good, and it decreases compile time, whereas execution time doesn't increase a lot. I think this direction is good, so I'd like to continue this work. Thank you for listening.